Hello everyone, this is Ruizhen Hu from Shenzhen University, and the talk I'm going to give today is about learning shape functionality and part mobility. One of the goals of computer graphics is to provide tools for designing and simulating real or imagined artifacts. While such artifacts are usually functional, and thus an understanding of functionality is paramount for simulating and validating different designs or artifacts. But what is functionality? The dictionary defines it as the particular use for which an object is designed. More detailed definitions are possible, such as the application of an object in a specific context for the accomplishment of a particular purpose. So essentially, functionality typically refers to the purpose of an object, or more specifically, how the object can be used to accomplish a specific goal. The important fact to note is that functionality pertains to the use or applications of an object, which is different from the object's geometry appearance. Of course, the shape of an object may have a strong relationship with its functionality, but the two are not identical. In this example, we see the difference of a shape similarity measure based on comparing the geometry of the shapes in the first row with the measure that compares functional aspects of the shapes in the second row. We see how one of the great advantages of functionality is that it allows us to find something in common between shapes with significantly different geometry, such as handcart and supermarket cart. One key difference between functionality recognition and object classification is that for object classification, the question to be asked is like, what is this? And the answer for the object shown on the left would be chair. While for functionality recognition, the question is like, what can we do with this? And we can see that, other than chair, this object can be used as a handcart and drying rack. From this simple example, we can see that, other than a single category label, an object can be used in different ways and serve different functionalities. But one thing to note is that not all chairs can serve the same set of functionalities as the left one. For example, this swivel chair may not be able to function as a drying rack. However, comparing to the left four-leg chair, it has more freedom on the part motion, and different parts can perform different types of motions, which we refer as part mobility, and is highly related to how it functions. So, following, I will introduce deep learning-based methods used to analyze shape functionality and part mobility. For static shape functionality, we consider it a combination of shape geometry and interaction, and the key is to model the involved interactions and analyze how the geometry and interaction are related. For more traditional methods, handcrafted descriptors are designed to represent the interaction. Take this table dishes interaction as an example. A descriptor called IBS, short for Interaction Bisector Surface, which is the purple surface here, is proposed to capture the spatial boundary between two objects. And another descriptor called IR, short for Interaction Region, is proposed to describe the geometry of the surface region of the central object corresponding to the interaction. IBS and IR together can provide a detailed representation for local static 3D interactions. For things involving multiple interactions, a contextual descriptor called icon, short for interaction context, is proposed to group similar type of interactions and organize them into a hierarchy. By co-analyzing the interactions around objects from a specific category, we can localize and analyze the properties to surface patches that support specific types of interactions. When given an unknown object, it can be used to predict the corresponding functional patches and compute a score of how well the shape and its patches supports the model functionality. However, as most of the traditional methods that rely on handcrafted features, the generality of the proposed method is rather limited. So, later in 2018, we proposed a deep learning-based method which can understand the object functionality by hallucinating the supported interactions. The motivation here is that humans can not only predict the functionality of an object given alone, but also hallucinating the interaction or usage scenario involving the object based on their knowledge and experience. So the main question we pose here is whether a machine can replicate this human capability to understand object functionality using hallucination. And in this work, we introduce predictive and generative deep neural networks, which work in conjunction and enable us to answer this question in the positive. Here, predictive means that we are able to recognize multiple functionalities of the given 3D object. And generative means that for each functionality label, we can generate corresponding interaction context to visually demonstrate the object's functionalities. Here is an overview of our method. Given a 3D object in isolation, we encode it as a voxel volume. Then our first network, the functional similarity network, or FSimNet, maps the given object to the scenes showing circle functionalities. FSimNet is then complemented by a generative net called EigenNet that synthesizes a voxelized surround from the object and its predicted label. Those two networks are further complemented by a segmentation network called ISegNet that separates the interacting objects into different groups according to their interaction types. In this manner, we can refine the scenes by retrieving high-resolution models to substitute the generated context. And our key contribution is the design of those three networks. To enable the learning process, we construct a dataset which contains more than 1,000 scenes with 25 different functionality labels and 18 different interaction labels. With such a dataset, our first goal is to map the given object to the scenes showing circle functionalities. To achieve that, we need to learn a functional similarity measure between objects and scenes. The design of our network follows the spirit of triplet network. The triplet network usually takes triplets as training data, which consists of an anchor, a positive of the same class as the anchor, and a negative of a different class. Then the network maps the triplet to the same embedding space to compute their distance. Intuitively, the triplet loss tries to minimize the distance between the anchor and the positive, and maximize the distance between the anchor and the negative. Note that the elements in a triplet are from the same domain. So, if we directly apply the triplet network to our problem, the input triplet should be either all objects or all things, which belong to the same domain. While, as mentioned before, we need to learn a functional similarity measure between objects and things. So for each object, we collect a positive thing, that is, a thing displaying the same functionality of the given object, and a negative thing, which is not, which for example means that the given object here can be used as a table, but not as a stand. Accordingly, we modify the original architecture of a triplet network to be able to map different domains into the same latent space. One subnet encodes the isolated object, and the other two subnets with shared parameters encode the same context. The loss is similar in spirit to the ones used in a triplet network to ensure a margin between the distance to the positive thing and the distance to the negative thing. But one thing to note is that in practice, an object can serve multiple functionalities. So to enable such multi-possibilities, instead of mapping the object to a feature point in the latent space, we map it to a distribution of that space and define the distance between an object and the thing context as the expectation. With a functional similarity measure, for any isolated object, we can retrieve the most similar thing context associated with functionality label. Here are some results. Note how our method can handle a variety of human-object interaction and object-object interactions. Here are some example results showing how we capture the multifunctionality. For example, on the second row, we can see interesting examples of stool-like lamp and handcart used as a chair. Given the isolated object and one of the possible functionality label, we achieve the hallucination in two steps: interaction context generation and segmentation. We use two steps because the interaction context label has much higher dimension and a more structural relation between objects with different interaction types that need to be considered. So it would be hard to generate directly with a relative small set of training data as we have right now. And we found that dividing the problem into two simpler subproblems makes it more solvable and the results are more stable. Let's first check the eigennet for interaction context generation. Here, our goal is to generate the corresponding interaction context for the given central object and functionality label. For the network architecture, the common way is to extract information from both inputs and then concatenate. But one thing to note is that our goal is to generate interaction context that reflects the functionality of the given object. But since they are both represented by 64 cubic voxels, the central object needs to be correctly skewed and placed. So, instead of generating the whole thing altogether with constraints on the central object channel, we directly learn a translation of the input object to place it in the right location with right size inside the same box, and generate the interacting objects in the other subnetwork to constitute the final scene context. Here are some generated context results. Note how the scenes generated for the objects are quite meaningful and adapt to the geometry of the objects, such as the giant rack and handcart. Then for the iSegnet, the goal is to segment the context voxels into objects that perform different types of interactions with the central object. Since we only need to segment the interacting objects, the central object channel is kept the same. The remaining segmentation network architecture is similar to that of the generation network, but with skip connection. So in this way, we get the final segmented scene context. Here are some segmentation results. We can see that our network is able to segment objects into groups that have similar interactions with the central object and identify the correct labels for the groups. In the end, we replace the segmented voxels in a scene with higher resolution models to get scenes with more details. More specifically, we retrieve objects from the scenes in our datasets, which are the most similar to each connected component in the segmented voxels. Once all the objects are retrieved, we subdue and translate them and place them around the central object to get the final scene. Here are some scene refined results. We observe how the segmentation into interaction types allows the post-processing to select meaningful objects to compose the scenes. For example, we can see that the orientation of the generated chair and screen are quite reasonable. Here are some more results. We can see for the basket, the generated bottles are correctly skewed and placed inside the bucket. For dynamic part mobility, more traditional methods also focus more on interaction characteristics. Just that now the interaction is on part level instead of object level. Here, the part level interaction is represented by a set of descriptors related to part relation and part geometry near the interaction region. Then, based on a static to dynamic mapping, objects with similar part motion While it's unrealistic to expect such an input, when functionality inference needs to be carried out over raw scans of a 3D environment, for example, during robotic navigation. So, we propose another deep learning-based method to deal with input, which could be a single, unsegmented, and possibly partial 3D point cloud, and be able to simultaneously predict movable parts and hallucinate their motions. To learn such part mobilities, we build a dataset which contains near 1,000 objects from 42 different categories. Each object has one or multiple moving parts. And for each moving part, we further annotate a set of part mobility parameters, including motion type, axis direction, and position. Here, 3 types of motions are considered, including translation, rotation, and their combinations. With such a dataset, the most straightforward way to learn the part mobility is to directly predict the part segmentation and the mobility parameters, and then the part motion can be generated based on the prediction. However, our key observation is that switching the prediction order, that is, hallucinating the part motion first, and then obtaining the part segmentation and per part mobility parameters based on the hallucinated motion, gives better results. Accordingly, our key contribution is that we designed a novel recurrent neural network called RPMNet for motion hallucination and motion-based segmentation, and another network called MobilityNet for mobility parameter prediction. Note that hallucinating and checking point-wise movement over time represents the most general form of motion prediction for point cloud input. This allows RPMNet to learn non-trivial motions beyond simple translation, rotation, or their combination, which is hard to be simply represented by a set of mobility parameters, like the umbrella example shown here. Moreover, to represent the motion, we introduce the concept of displacement between a pair of adjacent frames, where each arrow here indicates the moving direction with its color encoding the moving distance for each point. And the displacement between all other pairs of adjacent frames can be represented in the same way. We found that this kind of motion representation is more stable and more general to describe a variety of motion. Now, with a key representation of the motion, I can give more details about our method. First is the RPMNet. The core of RPMNet is a recurrent neural network that predicts displacement maps. Once the displacement maps are generated, they are concatenated and passed with the input point cloud to a segmentation module that provides a motion-based segmentation. In more details, given a point cloud as input, we use the encoder to create a feature vector and then fed to an LSTM that learns the relationship between the features and the temporal displacement. Afterwards, the output of the LSTM is decoded to obtain the displacement map. We repeat this procedure several times to obtain a sequence of displacement maps. Then we can add the displacement maps to the input point cloud to get the motion sequence. The loss for the motion hallucination network consists of two parts. The first is the reconstruction loss, which quantifies the reconstruction quality of both the point cloud and the displacement maps. Specifically, it measures the deviation of the point cloud from its original geometry after motion with the term geometry loss, and the deviation of the displacement map from the ground truth with the term displacement loss. The second part is the motion loss, which is used to ensure the smoothness of the hallucinated motion. More specifically, we constrain the displacement of each point to be consistent across adjacent frames by minimizing the variation. To pass the generated motion to the segmentation module, we first concatenate all the displacement maps. Then the displacement set is passed to fully connected layers that segments the shape into a reference part and a moving part. Then the displacement set is further concatenated with the input point cloud and fed to an encoder-decoder that extracts a set of point features. A pointwise distance matrix is then obtained by computing the distance between corresponding point features, and a clustering method is applied to further segment the points in the moving part into several moving components. Finally, we add the displacement maps to the segmentation result to get the motion for each moving part. The loss for the motion-based segmentation module is shown here. The first term is the object-level segmentation loss, defined as the softmax cross-entropy between the predicted and the ground truth segmentation. The second term is the loss for the finer segmentation of the moving part, which is defined as the distance matrix of the point feature. Now, with the predicted motion and segmentation, we can use the second network, mobility net, to estimate the mobility parameters to describe the motion. The input for mobility prediction is the segmented motion sequence, which can be considered as a combination of input point cloud, path segmentation, and the motion displacement set. Since the part motion is independent, we predict the mobility for each part separately. Take the left dot as an example. We take the corresponding set of displacement maps and concatenate it with the input point cloud to pass to an encoder and fully connected layers, then get the corresponding set of mobility parameters as illustrated here. The loss for the mobility prediction network ensures the correctness of the motion type, as well as the position and the direction of the axis for each segmented moving component. Here we show the prediction of other moving parts. Finally, we can get the mobility parameters for all the moving parts like this. In summary, our RPMNet first predicts a motion sequence with segmentation for the input point cloud. Then the mobility net estimates per part mobility parameters. Here we show the results of the object with single moving part. Our method predicts all rotational motion accurately on shapes with different axis directions and positions. For translation motion, our method is able to predict the correct direction along which the blade opens. Note that the small button also moves together with the blade during the motion. We can also predict motion that involves a combination of translation and rotation. Here, the head of the bottle is correctly rotated and translated upwards. Given an object with multiple parts, RPMNet can simultaneously predict the motion of all the moving parts. We can see that our method can correctly segment moving parts in several different configurations. For example, for the TV bench here, our method is able to recognize different types of motions and segment the two doors and the jaws into different moving parts. Our method can also perform hallucination for shapes with non-trivial motions. for the bow and arrows in the second row. The motion captures the translation of arrow as well as the shrinking of the ball string. Moreover, most previous methods cannot deal with such type of motion, demonstrates the generality of our method. Here we show that we can also apply our RPM net on real scans of objects. The upper row shows small objects scanned with an ARTEC EVA scanner, while the lower row shows objects scanned with a Microsoft Kinect. We can see here that even the scan is incomplete, our method can still predict reasonable motion. Here we show the mobility prediction result from MobilityNet. We see that the network is able to predict mobility parameters for different kinds of motions. For example, the translation of the drawers and the rotation of the doors of the desk. To conclude, is found. For shape functionality, we enable functional understanding and usage of hallucination of isolated 3D objects with the introduction of predictive and generative deep neural networks. The things exemplifying functional uses of objects generated by our AgentNet, including both human-object interaction and object-object interactions, and also adapt to geometry of the objects. For example, the generated context for the drying rack adapted to the different shapes of drying racks as well. And then, as a first step in functional analysis using deep neural networks, our work has several limitations and can suggest interesting directions for future work. Currently, the interaction context generated by our method are limited in terms of scene variation and complexity, as they are supposed to mainly demonstrate the functionality of one object. So, how to increase the diversity of the generated result could be an interesting problem to explore. It would also be interesting to extend the approach to generate larger and more complex things that display broad functionalities, such as a living room or a kitchen. Last but not least, we would also like to collect larger and more diverse data sets, such as objects with multi-functionalities, to explore more about the intrinsic properties of functionality. For part mobility, we introduce networks that can be applied to predict the motion and mobility of a single unsegmented and possibly partial 3D point cloud that represents a static state of an object. The network include RPMNet, a deep recurrent neural network that predicts the motion of shape parts and effectively partition all input point cloud into a reference part and one or more moving parts. And MobilityNet, a deep network that predicts high-level part mobility parameters that describes the potential motion of the moving parts detected by RPMNet. However, our network might provide incorrect predictions when the input geometry is ambiguous. For example, the network may generate imperfect motion sequence with outlier points when moving and reference parts are spatially too close, or produce incorrect part segmentation when two parts with the same type of motion are well aligned. like the two doors of a cabinet that open with the same range shown here. Another limitation is that our method currently is not able to hallucinate a forward and a reverse motion together, since adding the training sequence in both directions will cause ambiguity. It would be interesting to explore some more sophisticated solutions to this problem. In addition, our current dataset is relatively small, composed of less than 1,000 objects, and it assumes that the shapes are meaningfully oriented. Therefore, a direction to improve our method is for more complex scenario is to augment our dataset by applying random transformations to the shapes so that our network can operate in a post-invariant manner. We are glad to see that recently a realistic and physics-rich simulated environment that hosts a large scale set of articulated objects has been released, which can enable various robotic vision and interaction tasks that require detailed part mobility understanding. In the end, I would like to thank all my collaborators and students for contributing to those previous mentioned works. And thank you for your attention. I'm now ready to take any questions. Motion is transferred for motion simulation. However, the problem of this method is that the input needs to be pre-segmented into parts to model the part-level interactions.